So, you did it. You crunched all the data, you tuned the parameters, and you have a large language model that actually, well, works. And that's a huge step, right? But honestly, getting a model to just function, that's just the starting line. Today, we're going to move way beyond the basics. We're tackling the real-world challenges that turn a cool prototype into a professional, robust system. We're talking about making our models fair, understandable, efficient, and ready for whatever we throw at them. Let's get into it.
You've hit that point in the journey. The model's spitting out text, it's answering questions, but suddenly a whole new set of questions pops up. Is it fair? Can you really trust its answers? Is it actually fast enough to be useful for anyone? And on a physical level, how in the world does all this even work? These are the questions, that separate a fun weekend project from a serious production-ready tool.
All right, first up, the fairness question. This is where we step away from just the code and start thinking about the consequences. It's about making sure these incredibly powerful tools we're building are also responsible ones.
And this is a huge one, because let's be real, our models are trained on text from our messy, complicated, and often biased world. So it's no surprise they'll learn and sometimes even amplify those same biases. The real challenge isn't just trying to avoid unfairness, it's about actively building fairness into our systems right from the very beginning.
It all comes down to balance. This isn't just about getting the technically correct answer. It's about having some ethical integrity. Responsible AI development means we're making a conscious, deliberate effort to find and fix the biases that could lead to really unfair outcomes, especially in critical areas like hiring or loan applications or even healthcare.
So, where does all this bias even come from? Well, a lot of it starts with the data itself. If the model only learns from a narrow slice of the world, its view is going to be skewed. But it can also creep in from the model's own algorithm. Or it can show up as cultural and gender biases when a model just repeats the stereotypes it found in all that text it read. Just knowing these different types exist is the first step to fighting them.
Okay, so the good news is we have a game plan. First, you start by feeding the model a much more diverse set of data to give it a more balanced worldview. Then, you test it against specific fairness metrics to see how it actually performs for different groups of people. Getting human evaluators involved is also absolutely critical for catching those subtle biases a machine might miss. But here's the kicker. This job is never really done. You have to continuously monitor the model after it's out in the wild to catch and fix new issues as they pop up.
But look, fixing bias is kinda tough if you don't know why a model's being biased in the first place. And that leads us straight to our second major challenge, the transparency question. How do we crack open that AI black box?
This really cuts to the core of it, doesn't it? I mean, if your model denies someone a loan or makes a medical suggestion, and you can't explain why it did that, that's a massive problem. Trust isn't just about getting the right answer. It's about understanding the logic behind it. Without that, we're all just blindly following an algorithm.
And this is exactly where these fields, interpretable AI and explainability, come into play. The whole point here is to develop ways for us to peek inside the model's head and see its decision-making process. It's about turning a mysterious black box into a transparent system where we can actually follow the logic and, check its work.
And you can see how all these benefits just stack on top of each other. When we can see why a model made a choice, we naturally start to trust it more. That same transparency is what helps us spot those hidden biases we were just talking about. And when we understand the model's weaknesses, we can actually fix them and make it better. It all leads to accountability, which is just non-negotiable in fields like medicine or finance.
Okay, so our model is getting fairer, it's more transparent, awesome. But even the best model in the world is pretty useless if it's too slow or too expensive to run. So that brings us to our third big challenge, the efficiency question.
Seriously, you could have the most accurate ethical model ever created, but if it's too big to fit on a server, or it's too slow to answer a user's question in real time, it's not actually useful, is it? This is the constant balancing act in AI, juggling size, speed, and performance.
The main strategy we have for tackling this is something called model compression. The easiest way to think about it is like creating a zip file, but for your AI. The goal is to shrink the model size, make it faster, make it less resource hungry, all while trying not to lose too much of its accuracy. This is the magic that makes it possible to run powerful AI on smaller devices, like the phone in your pocket. So, how do we actually do this? Well, there are a few common tricks. Pruning is kind of like trimming a bonsai tree. We just snip away the least important connections. Quantization is where we reduce the precision of the model's math, which makes it smaller. And my personal favorite is knowledge distillation, where you have a big, smart teacher model train a smaller, leaner student model to copy everything it does. Pretty clever, right?
All right, we've talked about the model's ethics, its logic, and its efficiency. But what is all of this incredible software running on? Our final section gets down to the physical foundation, the hardware question.
You know, we always talk about AI living in the cloud, but that cloud is made of very real, very powerful computers sitting in absolutely massive data centers. Understanding the physical gear is key to understanding how these models can even exist in the first place. So, what are the actual nuts and bolts?
So, at the very heart of it all, you've got CPUs acting as the general-purpose brains, and GPUs as the specialized, heavy-lifting workhorses. Then they need huge amounts of super-fast memory and storage, all connected by high-speed networking. It's really like a symphony of hardware, and every single piece has to work perfectly together.
But if there's one component that has defined this whole AI revolution, it's the GPU. The reason is pretty simple. A CPU is a jack of all trades. It does one or two complex things at a time. A GPU, on the other hand, is a specialist. It can do thousands, even millions of simpler calculations all at the same time. And this kind of parallel processing is exactly what LLMs need to function, making GPUs unbelievably faster and, in the long run, more cost-effective for this kind of large-scale AI work.
So by looking at fairness, transparency, efficiency, and hardware, we're not just building a model that works anymore. We're building one that's genuinely better.
So let's just nail it all down. To build better AI, you really need to focus on these 4 pillars. First, fairness. You have to be proactive about hunting down and fixing bias. Second, transparency. You use explainability to build trust. Third, efficiency. You use compression to make your models practical for the real world. And finally, the right hardware to make it all run. That's the blueprint for building responsible and effective AI.
Hey, if this explainer helped you get a handle on the bigger picture of what comes next for LLMs, do me a favor and hit that like and subscribe button. Every share really helps us break down more complex topics just like this one. Thanks so much for watching. And I'll just leave you with this final thought. As we get better and better at solving all these technical challenges, the focus really starts to shift. The most important question is no longer about whether we can do something, but about whether we should, and having the wisdom and responsibility to decide how and where we deploy this incredible technology.